Okay, I broke this lesson into 4 sections: Intro to Electrons, Quantum Theory, Calculations, and Quantum Numbers. First section, Intro to Electrons. So electrons want 3 things. They want to be close to the positively charged nucleus, they want to stay as far away as possible from other electrons, and they want to have the smallest amount of energy possible. You need to know the Heisenberg uncertainty principle, and this has nothing to do with Heisenberg from Breaking Bad. But the Heisenberg uncertainty principle says that you cannot know both the speed and location of an electron at any given point in time. You can only know either the speed or the location. Okay, so the electron cloud contains 3 things. It contains the energy level, orbital, and suborbital. Energy level is going to correspond to the periodic table row number, so I just wrote PT row number, but the periodic table row number. So, for example, if the little black dot in the middle there is my nucleus, this would be energy level 1, 2, 3, 4, 5, 6, 7. So your energy level is going to be that row number, and 1, this is going to be your lowest energy. And anything in the 7th energy level, that is considered your highest energy level, or high energy. Okay, so you've got your energy level, then you've got your orbital. Each orbital has a shape, S, P, D, and F. S stands for sphere. P is for peanut. D is for dumbbell. And F is for flower. And it's just kind of the shape of what the orbital looks like, and I'll show you that in class. And then suborbital, so every orbital has a certain number. So S, you can have 1 S orbital, you can have 3 P orbitals, you can have 5 D orbitals, and you can have 7 F orbitals. And then also each suborbital can hold 2 electrons. Alright, so for example, if you can have 7 F orbitals, that would correlate to 14 electrons, because each of those 7 can hold 2 electrons. So to determine how many orbitals are in an energy level, use n squared to figure that out, where n equals the energy level. For example, if you had energy level 2, so n is your energy level, so our equation is n squared. In this case it would be 2 squared equals 4. And so energy level 2 has a total of 4 orbitals. So you just use the n squared to figure that out. To determine how many electrons are in an energy level, use 2n squared. So for example, I said energy level 2. And so our n is 2, and 2n squared would be 2 times 2 squared, and this equals 8. Oops. 8. So energy level 2 can hold 8 total electrons. Alright, next section on quantum theory. We know that electrons exhibit wave-like properties, and this allows them to emit light. So elements emit light when energy is added to them. We call energized electrons excited. So there's a couple terms here. Ground state. Ground state refers to the lowest energy level of the element. And a quantum of energy. And a quantum of energy is a certain amount of energy needed to move the electron from its ground state to an excited state. So from its lowest energy level to an excited state. So let's look at an example here. I just drew part of the structure, so this would be energy level 1, energy level 2, energy level 3, and energy level 4. And if I had an electron that was originally right here in the first energy level, and that was its ground state, if it wanted to jump up to the second energy level, or even the third, or even the fourth, that would be an example of it becoming excited. So energy is added, specifically a quantum of energy is added in order for it to move up into an excited state. So we can't necessarily see that happen, but what we can see is when it jumps back down. Okay, so then this electron is going to then jump back down from its excited state because it can't stay in its excited state forever. And so when it jumps back down, this is your electron. When it jumps back down, it emits light waves. And we can see this. So the way that we can see that is depending on the wavelength of the waves that it emits. We might see red, we might see orange, we might see violet. Okay, so those lights, those colors are caused by energy levels, excited electrons. They're caused by electrons that have been excited and that they're then moving back down to their ground state. So once they move back down, they emit the light that we can see. So you don't have to write this down, but this is just to show you all the different waves that we know about. And you can see that it's a very small section right here that makes the visible spectrum of the colors that we see. So all of these colors, it depends on, the color depends on the wavelength. So for example, if the wavelength was 400, you would see blue. If the wavelength was up to 700, you would see red. And so it depends on the wavelength of the energy that is emitted, and that will determine the color that you see. Alright, the next section is calculating this upside down y thing. That is called lambda. This thing right there. So that stands for the wavelength. So lambda is the wavelength, or the upside down y, and frequency. So these are the three equations that you need to know. So speed of light equals wavelength times frequency. That one you will be given speed of light. This is a constant, it's always the same. But just so you know, this number is 3 times 10 to the 8th power meters per second, or 3e8. So speed of light is always going to be that number. And now if you look down at the second equation, we're using something h called Planck's constant, and it's kind of like your 6.02 E23. It's just a number that's always going to be the same. This will always be given to you also, so you don't need to memorize this. But Planck's constant is 6.626 times 10 to the negative 34th power of joules per second. Okay, so this obviously you can write as 6.626 e negative 34. So when you're using these calculations, speed of light is always going to be the same, and I'll give that to you, and Planck's constant is always going to be the same, and I will give that to you as well. F always stands for frequency, and it just depends on what it is asking you to calculate for which equation to use. And we are just going to practice these in class. Just take down the equations and what each variable stands for. The last section is quantum numbers, and this is going to be super confusing until we actually do it with while looking at your periodic table. And so I just want you to copy down what is on here. You've got N, L, M of L, and MS. So that order is always going to be the same. You're always going to have your numbers listed in this order. So N stands for the principal quantum number, which is just the energy level occupied by the electron. So energy level, we know this is the periodic table row number. L stands for the angular momentum quantum number, and that is a fancy way of saying the shape of the orbital. So L just stands for the shape of the orbital. Is it an S, P, D, or F? And depending on the shape, it's going to have a specific value, which is listed here. ML stands for the magnetic quantum number. This describes the orientation around the nucleus / suborbitals. And again, just copy this down and we will look at a periodic table and it'll all make sense in class. But depending on your orbital, it determines what values you can have for your ML quantum number. And the last quantum number is MS, spin quantum number, and this describes the spin of the electrons. It can have two directions, either clockwise or counterclockwise. If it is clockwise, it is positive 1/2. If it is counterclockwise, it is negative 1/2.